Seamless virtual engineering is the cornerstone of Germany's Industry 4.0 initiative. In this video, EPLAN, Rittal and Phoenix Contact present the end-to-end digitization of product manufacturing in 3 dimensions. From the top floor to the shop floor, this describes our collaborative approach in engineering, in control cabinet and switchgear enclosure systems, and in automation technique.
A complete digital model of system components enables efficient, automated engineering and manufacturing. This means that all relevant product attributes must be described and stored in standardized digital formats from the product development stage onwards. A key outcome of the product development process is a 3-dimensional model of a specific component, in this case of a double-level terminal block. All key component attributes are visible on the model, for example, places where labels need to be attached, where jumpers can be inserted, and where wires can be placed. However, this information must be available in machine-readable form to enable automated engineering and production. To this end, we employ the classification standard E-class and describe the location of the product attributes using the system's vocabulary. It is now clear exactly where the attributes are positioned within the model. So the end result is a 3D model and a complete set of E-class classification data. This includes standard information, such as the manufacturer's name, product code, and simple geometrical data, as well as additional details, for example, 3D coordinates for connections. By saving data on relevant component attributes in the standardized and exchangeable E-class format, it is easy to make information available for configuration tools, online shops, and engineering systems. One of the tangible and lasting changes that Germany's Industry 4.0 initiative will bring is the end-to-end digitization of processes across the entire value chain, including engineering, materials management, and manufacturing. In this context, it is important to highlight the potential offered by the integration of engineering tools and data models. What's more, this integration can already be put into practice today. The key to integration across all aspects of the value chain is product data. Product data that is highly available and compatible with all systems and processes. Standardization of digital product information and making it available for diverse applications is one task. Making the data compatible with multiple systems and integrating it seamlessly into the customer's value chain is another. To this end, EPLAN provides data from manufacturers including Rittal and Phoenix Contact via the EPLAN data portal. This global web service provides EPLAN customers with access to information on more than 500,000 products from nearly 80 manufacturers. The service is tightly integrated with EPLAN's development tools, allowing users to search the data portal for key functional criteria, to identify suitable products, and then seamlessly incorporate these products into their development environments. By leveraging standardized EPLAN interfaces, for example for ERP and product data management systems, it is possible to enrich this product data to include further information. For example, order numbers, defined times for work tasks, and prices. This enriched information is then available for use in engineering, materials management, and manufacturing. In the engineering stage, the product data is employed to create a functional description, that is, a schematic diagram. This is then used as the basis for building a 3D model that incorporates all information required for downstream production processes.
Moreover, this model contains all data needed for machining operations, for wiring, and for creating pre-cut and pre-assembled cables. Defined machine interfaces are able to analyze and process this data and transfer it to existing manufacturing systems. Following the virtual assembly of components in the enclosure, the digital product data can be used to determine the total power dissipation of the control cabinet application. EPLAN transfers this data on power dissipation, plus key information on voltage, the enclosure location within the factory, interior and exterior temperatures, and nearby media to Rittal Therm. Rittal Therm is a software program used to design and size heating, cooling and climate control solutions for switchgear. Information on the selected cooling unit and corresponding accessories is transferred to the EPLAN platform, combined with the product data in the EPLAN data portal, and then incorporated into the virtual prototype.
The virtual prototype is now fully digitized and is ready to be used in downstream processes.
Automation is increasingly essential to switchgear manufacturing. As we can see at this station, digital data from the virtual prototype is used to fabricate a physical component. And this is now established practice and puts key aspects of the Industrie 4.0 initiative into action. End-to-end digitization from design to the product equipment, fully automated machining, and the use of engineering data at all steps in the value chain through to manufacturing. Let's now take a look at the machining tasks. To this end, we take our virtual prototype, which we created earlier at the virtual engineering stage. Here, we can now see all relevant machining information. That is, we can see what tasks need to be performed where on the mounting plate. And that's not all. We see where threads need to be tapped and what tools are required for our machining tasks. All information is now in the virtual prototype. We simply have to send the data to the production equipment, and it can then complete the required task. The data has now been transferred to the equipment's control unit. We can put the mounting plate into position and push the start button.
In addition to allowing the integration of existing automation technologies, the Smart Engineering and Production 4.0 concept grants us a glimpse into the future of manufacturing in the spirit of the Industry 4.0 initiative. The virtual prototype provides us with a digital description expressed in Automation ML format of a terminal block, comprising a support rail, terminals, accessories, labeling and jumpers. This Automation ML-based description is then read and interpreted by a smart production control system.
The information from the virtual prototype is then used to provide data and parameters to the individual processes within a modular production line. We can then initiate fabrication of the terminal block by means of the production control system. The first step is to cut the support rail to the defined length. This support rail is then transferred to a robot. The robot is equipped with magazines containing a variety of terminals. The terminals are then mounted onto the support rail in the predefined sequence. Then a unique ID number is written to the RFID tag that is attached to one of the terminals. The first process step is then complete, and we have our terminal block.
Zur eindeutigen Identifikation ist sie mit
The
einem
next step is to attach the labels and to insert the jumpers. In this instance, we are leveraging the information from the virtual prototype to support a manual task. We read the data from the RFID tag on the terminal block and use it to generate the corresponding print job, which is sent automatically to the printers to output the labels. At the same time, the information required by the production worker is displayed on the screen, explaining where the labels and jumpers are to be positioned on the terminal block. The labels and jumpers have now been attached to the block in accordance with the definitions of the virtual prototype, and the block is now fed to the next step, visual inspection. The final step is quality control in the shape of a visual inspection. Once the RFID tag has been read, a vision system captures an image, and this image is compared with virtual prototype. It is then immediately clear whether or not all components are in the correct positions, and if all the jumpers and labels have been correctly attached. Here we can see that all production and assembly tasks have been successfully completed.
An important role is played by the dedicated EPLAN machine interfaces. These allow the seamless integration of current and future automation technologies into the digital production development and manufacturing processes in line with the Industry 4.0 vision.
In addition to the mechanical tasks and smart component manufacturing, other forms of automation are possible. In switchgear production, for example, many processes are still manually performed, such as the assembly of terminal blocks and wiring. These processes could be streamlined by employing digital information in a virtual prototype. Here you can see future technologies for switchgear manufacturing, visual support for manual components assembly, and visual support for manual wiring. You'll recall we have just assembled the terminal block, and we now have all the information we need indicated on the block. We now want to know just where on the mounting plate we need to place the terminal block. We scan the RFID tag, and it tells us the position. In addition, we receive guidance on the block's orientation. In other words, we know the anchorage point, and it's marked precisely here on the mounting plate. We have now inserted the terminal block, and now we can turn to the wiring. We already looked at wiring during the virtual engineering process, and we have cut the wires to length and attached the contacts. Now we want to know where we need to position them. So we go to the wiring function, and the first thing we see is an overview of the various wires. That is to say, what wires follow what paths. We want to know which specific wire is to be placed where. I go to the function, Wiring in Steps. And now we can see that wire number 1 is to be routed from here to the terminal block, and that it has to be hooked up to connection point number 1 on the block, and to connection point 32 on device K32. We take the corresponding pre-assembled wire. All the cut-to-length wires are attached to each other in the right sequence on the reel. So we take the first wire and route it according to the instructions on the display. We do the same with the other wires, and in the end, we have installed all the wires as planned in the virtual prototype.
The digital information in the virtual prototype also provides a basis for fully automating tasks that are currently manual. An example is the fully automated wiring of mounting plates.
The availability of data from end to end, from engineering to the actual production system, enables significant improvements in terms of both quality and quantity. The increasing digitization and virtualization of components and products enables further forms of automation and the enhancement of processes and technologies. The availability and seamless integration of relevant product information is one of the prerequisites for Industry 4.0.